Hi, welcome to this video where we'll be describing and discussing the Hartree-Fock method, in particular the Born-Oppenheimer approximation, and how this leads to an independent particle method which simplifies the electron moving in a potential field, that is to say the many electrons moving in a potential field problem. So without further ado, let's go. To begin with, we are going to be discussing the Hamiltonian and how this looks. The Hamiltonian of a system of n electrons and k nuclei with Zn charges is given by the following equation, where the first term is the kinetic energy of the electrons, the second term is the kinetic energy of the nuclei, the third term is the Coulomb repulsion between the electrons, and the third term is the Coulomb attraction between the electrons and the nuclei, and finally the last term is the Coulomb interaction, in other words the Coulomb repulsion between the nuclei themselves. This system of wave functions depends on the positions Ri and Rn of the electrons and the nuclei respectively. So the positions of the electrons and the nuclei is what this particular equation or this particular wave function or this particular Hamiltonian depends on. We notice that given how large this equation looks and how difficult it is impossible to solve for the stationary Schrödinger equation for this particular Hamiltonian directly, which means approximations are necessary. So we must perform approximations, and the first step to do this is to separate the degrees of freedom connected with the motion of the nuclei. So we have to use the Born-Oppenheimer approximation. In this approximation, we assume that the nuclei is stationary. Having done so, we shall see that the electrons would then be able to adapt themselves to the current and new configuration of the particular system and structure. We see that this approach leads to a Hamiltonian for the electrons, which are in a field generated by the static configuration of the nuclei, and therefore a separate Schrödinger equation for the nuclei where the electrons have an energy that is seen as a potential is then determined or then observed to exist. So we then have this particular Hamiltonian called the Born-Oppenheimer Hamiltonian. So we see, having used the Born-Oppenheimer approximation, we've eliminated from this particular equation the the nuclei effects. So we have the first step as the kinetic energy of the electrons, but we no longer have the kinetic energy of the nuclei. We have then the second term being the Coulomb repulsion between the electrons, and then we also have removed the nuclei-nuclei interaction, and we are only left with the nuclei-electron interaction, which is the third term, which is the Coulomb attraction between the electrons and of course the nuclei. We also see that the motion of the nuclei is neglected, and therefore only the electrostatic energy of the nuclei is added or considered. So we only add that to get the total energy of the system. The nuclei are also treated in a classical fashion, and their ground state energy corresponds to a minimum potential energy. So we see that quantum effects are neglected. Now, even though we have now assumed the nuclei to be stationary, we still have the problem of solving for the electronic structure, and given the above equation, this still remains to be a difficult task. And so we have to then approximate the eigenfunctions of the Hamiltonian. because the second term, as we have already mentioned, which is the electron-electron interaction, still has so many degrees of freedom. So the problem is still difficult. So we have to then approximate the eigenfunctions of this particular Hamiltonian in order for us to then be able to solve it. And we have so many approximation methods that actually exist for the purpose of trying to solve this Hamiltonian. So this particular Hamiltonian, as we have already discussed, with all its terms, which we have now completely discussed, as we have said, there are many ways to solve and to approximate the eigenfunctions. Now these approximations are, firstly, the many electron problem that we have is reduced to an uncoupled problem. We also have that the interaction of single electrons with another electron is accounted for in an averaged way into a potential felt by it. So this is the second approximation that we can use. This then results, of course, in an uncoupled independent particle Hamiltonian, which is given by this particular equation. So we have the first term, of course, under summation being the kinetic energy, and the second term being the potential energy. That potential energy is a new term we are going to introduce, and this potential energy depends on the positions Ri of the nuclei. It is quite complicated. We also see that this potential energy depends on the wave function psi, where this independent Hamiltonian particle Hamiltonian acts on. So we see that having defined all these things, V is quite, this particular potential is quite complex. So it is a non-local operator, which means that the value of V psi, or in other words, the value of V acting on the wave function psi, can be evaluated or is to be evaluated at a particular position R, which is determined by the value of psi at other positions R which are not equal to R prime, or some other positions. In other words, R not necessarily equal to another position R prime. In other words, we are saying at unique positions of R. And we see that that particular potential will also often depend on the energy in some approaches. And this is the price that we have to pay for an independent electron picture. And with that, we shall conclude on the second part of the Born-Oppenheimer approximation and how we see it leads to an independent electron picture. So without further ado, do not forget to subscribe. Please like and share and hit that subscribe button, and see you on the next video.